Hello, everyone, and welcome to our podcast. Today, we're diving into a fascinating new study about black carbon aerosols, how their mixing structures shape radiative effects, and how new modeling methods give us far more accurate assessments of climate impacts.
That's right. This study was led by Zhejiang University, together with the University of Manchester, Cornell University, and others. The authors include Professor Wang, Professor Zhang, and Professor Li. Truly a heavyweight collaboration.
So, when climate models simulate the warming effect of black carbon, where does the biggest uncertainty actually come from?
Well, black carbon is extremely powerful at absorbing sunlight. It directly heats the surrounding air, a major driver of warming. But once BC mixes with other particles like sulfates and nitrates, it gets coated, and those coatings dramatically change its radiative properties.
So the mixing structure is absolutely critical.
Exactly. But most climate models oversimplify it. They assume simple core shell structures or averages. That misses the true diversity of mixing states in the real atmosphere, leading to huge uncertainties.
And how exactly do those properties change? Why do past models fail here?
It comes down to two factors: coating thickness and the embedded fraction, how much of the BC is buried inside the coating. These depend on emission sources and aging. For instance, BC from industrial smoke ages differently than BC from vehicle exhaust, and those differences can greatly alter its warming effect.
Wow, that sounds incredibly complex.
It is. But older models simply didn't capture this. They reduced everything to neat averages, ignoring real-world variety. That's why results had major biases.
So how did this study solve it?
They built a state-of-the-art 3D optical modeling system. It links electron microscope images of particles, radiative transfer models, machine learning, and even the community Earth system model. Together, it reproduces the true complexity of BC mixing and its radiative effects.
And the results? Were they dramatic?
Absolutely. When realistic mixing was included, the simulated direct radiative effect increased by as much as 31.6% in polluted regions. That's a huge correction. It proves we've been systematically underestimating BC's warming impact.
Incredible. That's a massive difference.
Yes, and they also found that thicker coatings and higher embedding ratios make BC even stronger as a heater. It underscores how vital it is to capture BC's complex structures, especially in polluted regions.
So cutting BC emissions isn't just about climate, it's about health too?
Exactly. BC penetrates deep into the lungs, harming human health. So reducing it brings immediate air quality and health benefits, plus long-term climate benefits. Solutions include clean energy, electric vehicles, public transport, and cleaner industrial tech.
But those solutions are tough to implement, right?
Very tough. Clean energy requires heavy investment. Some regions lack infrastructure, and shifting people's habits away from private cars takes time and awareness.
Looking forward, what excites you most in this field?
Two things. First, more precise studies on aerosols beyond BC to capture their climate impacts. Second, global cooperation. Climate change is a shared challenge, and only through international action can we succeed.
So to wrap up, today we explored the complex world of black carbon aerosols, their mixing structures, their underestimated warming power, and why emission cuts matter more than ever.
That's right. Thanks for listening, and we'll see you in the next episode.
Bye-bye.